Welcome everyone to today's Virtual Digital Economy seminar. Thank you all for tuning in today, and it's great to see so many familiar faces again. And the moderator today will be Daniel Erschoff from the Toulouse School of Economics, and he will introduce our guest in just a second. As always, let me remind you about some organizational details very briefly. Please send any clarifying questions to everyone in the chat window throughout the talk. Daniel will manage the queue and interrupt speaker at a convenient time for you so that you can ask the questions. And if you prefer, Daniel can also ask you the question for you, and we will collect all the remaining questions for the Q&A after the talk in the general chat. So then don't hesitate to post questions at any point in time. So today's session will also be recorded. So if you do ask a question in person, you will also appear in the recording. And with that, I'm going to hand over to Daniel.
Great, thanks, Reinhold. So today we're very happy to have Ksenia Shakhgildyan from Bocconi University to talk to us about artificial intelligence, algorithmic bidding, and collusion in online advertising. So Ksenia, the floor is yours. You have 45 minutes plus 15 minutes for Q&A. Very much looking forward to this talk.
Thank you so much, Daniel, for your introduction, and thank you everyone for joining. I'm super excited to be here. Thank you for the organizers to invite me, and with this, let me start today's presentation. So I will present today on artificial intelligence, algorithmic bidding, and collusion in online advertising. This is a joint work with Francesco De Carolis, Gabriele Rovegazzi, and Michele Rovegazzi. And some of my co-authors are online here today. So guys, please chime in if you have something to add to my answers on the questions. Okay, so today I would like to talk about the internet advertising market in general. So this is a very large and on top of this, very fast growing industry. Let me just give you a couple of numbers. Revenues for 2012 for this industry were like 140 billion US dollars only in US. So you can imagine how big is it globally. And it grew by 12% from 2019 to 2020. And moreover, it continues to grow. Among all advertising formats that are available for the advertisers, sponsored search auctions is the most prominent segment of internet advertising with 42% revenue share. So how do these sponsored search auctions work? Every time a user enters a query on Google or Yahoo or Bing or any other search platform, for example, I enter car rentals in Berlin on Google. So as you can see here on the slide, a multi-unit auction takes place among the advertisers who submit the bid on the corresponding keyword. So the keyword can be a bit different than the user query. For example, the keyword for the advertiser could be Berlin rentals or just car rentals, but then the advertisers are aggregated and matched to the specific user query. And then the auction takes place among those advertisers. All ads are then ranked by the platform, and the ads with the highest ranks assigned are seen by the users as sponsored links at the top of the results page. For example, here Expedia took the first slot because it was ranked the highest, and then the sixth was ranked the second highest, and maybe so on. So there are a lot of auctions happening every millisecond, as you can imagine. It was estimated that almost 100,000 searches happen on Google every second. And hundreds of thousands of advertisers bid to capture users' attention via the targeted ads. Of course, this cannot mean that a human decision maker is behind all of these advertisers' bids. Most of the biddings, indeed, in online advertising nowadays happen through the artificial intelligence algorithms. This process has brought about substantial benefits in terms of the efficiency of bidding, the efficiency of how prices can react very fast to different demand and supply condition changes, but also created new challenges and questions for both the advertisers, the bidders themselves, and at the same time, regulators and the platform. The current debate on algorithm of collusion has identified two main channels through which the algorithmic pricing might enhance collusive behavior in this market. So first, the artificial intelligence algorithms might lessen competition because they can increase ability to react fast and aggressively to the changing conditions, thus making collusive strategies much more stable. At the same time, the second reason is that by using automated mechanisms that can be actually very similar for different advertisers, and by implementing common practices and optimizing the joint profits, the algorithms can lead to the same outcomes of traditional cartels without actually coordinating and just through the tacit collusion. So that is one of the main concerns that was discussed very broadly in relation to different artificial intelligence algorithms in different marketplaces. But in our context, moreover, at the same time, platforms themselves can decide how much information about auction rules to reveal to the advertisers. So recently, very hotly debated phenomenon, for example, in the workshop organized by European Commission, it was discussed by both the industry experts and the policymakers, is the fact that is called data fogginess, which means that nowadays less and less data, both just amount of data and the types of data, are available to the advertisers. So the platforms seem to reveal less and less data to the advertisers. For example, in 2019, Google decided to stop share the exact position of the advertiser, and they only now share whether the advertiser is on the top or at the bottom. Why this is important? This is particularly important because different artificial intelligent algorithms require different amount of information on auction rules. In this paper, we are focusing on the two types, but in general, there are some algorithms that require very little knowledge about the auction rules and auction environment. For example, the Q-learning approach that we use in the paper, because it optimizes the bidding behavior without actually knowing the economic environment, solely based on trial and error and taking the rewards as given. So how it works in just 2 words is that when the algorithm submits the bid, then the outcome that it sees is only the reward that it gets. And then it experiments by submitting another bid and getting another reward and so on. So it's trial and error experimentations. At the same time, there are other algorithms, for example, the neural network approach that we also use in the paper, that require knowledge of the specific auction environment because it requires knowledge of counterfactual rewards. What does it mean? It means that after submitting a bid and receiving a reward, the algorithm itself, after that, is able to calculate the counterfactual reward, which means that how much the algorithm would have earned had it submitted a different bid. Constructing these counterfactual rewards require the knowledge of the auction rules, the competitors' prices, the positions, number of clicks, and a lot of information about the auction formats. What is crucial here is that less information available to advertisers might shift the value generated by the advertising in general, by the digital advertising market, away from the advertisers and to the platform. And on top of that, it might influence the allocation efficiencies. Given these considerations, we focus on the following research questions, but let me first tell you about our strategy in general. So we evaluate the main questions using the series of 6 experiments, which we take from the theoretical literature. So we have specific 6 examples from theoretical literature on which we estimate the auctions model using different artificial intelligence algorithms. And this is approach which we follow the pioneering paper by Calvano and co-authors since we have no theoretical predictions of how exactly the algorithms would behave in these settings. So we use both Q-learning and neural network approach that to study what is the impact of the artificial intelligence bidding on the both generalized second price auction, the most popular format in the search auctions, and the weekly click growth mechanisms, VCG, I would call it later. And in particular, we focus on the several scenarios. So we start by considering the case of independent bidders deploying the artificial intelligence algorithms for bidding. Since there is no theory, even in machine learning, that tells us even whether there would be convergence in the case of multiple bidders learning at the same time the optimal strategies, the first logical question is whether there is actually convergence towards the Nash equilibrium predictions. And on top of that, since, for example, in the GSP auction, it's very well known that there is a multiplicity of the equilibrium. Even if we find convergence, the question is, do we converge to the Nash equilibrium? And if yes, then to which Nash equilibrium? So here I will give you the hint of the what we find, but I won't discuss the results so far. The next question, if we find convergence, is whether it's true that the artificial intelligence algorithms that require more information about the bidding process, so they are more sophisticated, actually lead to the improved efficiencies and decrease the Ksenia revenues. Are they better for the advertisers, the algorithms that are more sophisticated? And moreover, the very relevant for the policy making question is whether the algorithms sustain collusive outcomes. Moreover, since we focus on and contrast two different types of auctions, we want to see whether there are any differences that are predicted for those two. Since actually in theory, in the most used competitive benchmarks, we know that theoretical prediction tells us that the Ksenia revenue would be the same in those two. But is it true when the algorithms instead bid? After figuring out the answers to these questions for the case of independent bidders, we move on to several extensions that are actually phenomena that are often observed in the data. So we construct the experiments by introducing, in addition to the independent bidders, an extra noise bidder, or the bidder who randomly plays the strategies from all possible strategies. And this is a very common reality that you don't observe only the sophisticated bidders. There is often seen some randomness. So how would this affect the bidding? And the theoretical prediction would tell us that actually the efficiencies improve when there is the random bidder. All right, the next extension that is also very common, and recent literature, theoretical literature also looked at this case, is the presence of the intermediary. So nowadays, many bidders bid not by themselves, but actually through the intermediary, through the digital advertising agency. And it happens that in many auctions, it could be the case that the same intermediary plays for several advertisers in the same auction. What does it lead to? It is one of the incentives for the bid coordination. And it could be that the intermediary, by coordinating the bids of its clients, as a result, leads to lower Ksenia revenue as well. So we introduce this common player that would bid for several agents in our experiments as well. Moreover, the third extension that we consider, and we are very excited about, we are actually working now on this case, so it's still work in progress, is the case of asymmetric information. We all know that nowadays, for example, Google provides its own platform for the advertisers to bid in the auctions. And in this case, it's fair to assume that Google has much more information about the auction structure than the advertisers themselves. So at this point, we consider the case when just different players have different amount of information, and compare whether it's true that the more informed players would get more reward or less. Maybe I will pause for the second, just in case someone has a question already.
So I have a question. Steve, let me give Steve the floor. Yeah.
Oh, thank you, Daniel. One quick question. You mentioned briefly the random player. I wonder if you're thinking of this as something like entry, right? Because from what I recall, there's a nice kind of counter result in a more recent paper by John Asker, Chaim Fershman, and Ariel Pekis, where when they take the framework of algorithms colluding in markets, and once you introduce entry, things start falling apart pretty quickly. So I wonder if that's what you're trying to do here with the random player, if you're thinking of this as entry.
Thank you very much, Steve. Yes, I think it's a very relevant point. Yes, I think most of this randomness appears when the new bidder enter in the auction and start to experiment with different bids without actually learning already what is the strategy. So yes, it's definitely related. I think that we see it mostly when new bidders appear. Yes, but for now, it's really stylized experiments that we consider, we edit, and then we see how algorithms would behave in the presence. Thank you very much. Yes.
And
yes, Daniel?
Yeah, so I guess besides the amount of information that are required, Q-learning is kind of this forward-looking algorithm, like it's dynamic, essentially. But neural networks are basically these like adaptive algorithms that can be more static, so that can inherently limit how much they generate collusive outcomes. So I guess you specify the neural network in a particular way, but maybe I'll just leave that to you.
Yeah, sure. No, I actually don't go into big details here, so I'm happy to tell you a bit. It's true that the algorithms are different per se. To address this, we look at the case with discount factor being 0 in the case of Q-learning, so that we have same objectives in both. At the same time, we test the results based on the Q-learning that is known as synchronous learning, which actually also uses much more information than standard Q-learning. But so we test those two settings to be able to more cleanly kind of separate the effects. At the same time, thank you, yes. At the same time, we feel like these two algorithms that we consider, they're really the most common and kind of first thing that would come to mind of the advertiser to use, since in case there is no information, there is no other way but using trial and error algorithm. And if there is a lot of information about the structure, then it's much kind of more informative to straight away use the algorithm that is based on the loss function minimization. And if you can calculate what would have been the optimal strategy, then the calculation of the regret is much more kind of intuitive way to address this. That's why we for now focus on these two algorithms. Okay, but thank you for the questions. All right, let me move on. Okay, so let me briefly discuss what I'm going to discuss in the rest of the presentation. I briefly address the literature review, then I remind you about these two basic auction models that we consider. Afterwards, I move on to the substantial part, starting with the simulation of the results for the independent advertisers, and then I will look at the extensions that I already mentioned. So since we don't have too much time, let me be brief in terms of literature, but the slides would be there, and I'm happy to share as well. There are two broad strands of literature that we are related to. First one is the literature on the online advertising and bidding models. So this is definitely literature with a long history, looking at different auction formats, at different environments like complete information, incomplete information, presence of the intermediary, random player. And this is the literature from which we take the examples that we then bring to the experimentation. And the second broad literature that now it's very much growing is on artificial intelligence and its impact on the marketplaces. So the first block here is on the artificial intelligence pricing. So as I already said, we were inspired by the paper by Calvano and co-authors. There is a very nice paper by Daniel and co-authors on the artificial intelligence presence in the gasoline market. So a lot of markets now actually use artificial intelligence, but like even insurance market and so on. But more focused literature on what we are looking at is the literature on artificial intelligence auctions. And there are several papers in machine learning literature already. But the most relevant paper to us is the paper by Martino Banchio and Andrei Skripach from Stanford, but they look at the different auction settings as well. All right. Now, please bear with me for the 2 slides where I remind the auction rules. So here, we consider in our experiments different number of advertisers. Actually, in experiments, we look at the advertisers from 2 advertisers to 5 advertisers. They are denoted as I here in the slides. The positions also can be different. Number of positions in experiments that we look at, they range from just 1 position to 4 positions. We always consider the case when the number of positions is either the same or less than the number of advertisers. The slots, advertising slots, are ordered by the click-through rates. So click-through rates are denoted by X here. It is fair to assume that the click-through rate on the first position is much higher than on the second, and so on. And this is what we often observe in the data. So users are much more likely to click on the first ad position. Moreover, we will consider the cases of very asymmetric advertisers. So advertisers can have different valuations for the click. It could be if I am Expedia, car rentals in Berlin might be very highly valuable for me. But maybe if I am some other company not that related to the car rentals in Berlin specifically, then it won't be as relevant, the user click. So the advertisers would be ranked from them, ordered from the advertiser with the highest valuation to the advertisers with the lowest valuation. First bidder values the click the most. Bidder I submits the bid BI, which in the experiment would be actually on the grid. So we also do different variations. We try to vary number of points on the grid, number of possible actions, the grid itself, but this would be a positive number from minimum to maximum bid. The kth highest bid would obtain the slot number K, and then it would receive the expected utility, which would be its valuation multiplied by the click-through rate for the position that it received. The difference now between the GSP and the VCG formats is in their payment rules. So in the GSP, the bidder in position K pays the price per click, which equals to the next bid below him. So it would be bid number K plus 1 in this case. As a result, the payoffs are represented by the value per click minus the bid of the next player multiplied by click-through rate. And in GSP auctions, I already mentioned there is multiplicity of equilibrium, but one very commonly used benchmark, competitive benchmark, is what is called the envy-free equilibrium or EOS equilibrium by the names of the authors, Edelman, Ostrovsky, Schwartz. And this is why it's envy-free equilibrium, because the bidder is indifferent between bidding what it bids now or bidding to get the position above him. And as we can see here, the only thing to note is that actually here it's not truthful bidding, right? It's the bidders less than the valuation. Now the VCG. VCG has a bit more complicated payments rules where the bidder pays total allocation externality that he imposes on others, meaning that what would be the difference between the payments for the other bidders in the particular auction versus the case when the bidder just exits. And as we can see here, the utility is represented by the value multiplied by click-through rate minus the allocation efficiency. Actually, one of the reasons why Google was saying that they don't try to use the VCG now is this complication of the allocation rule, hard to explain to the advertisers what is actually the payment. But what is important here, and what is not very well seen right away, is that actually the revenue that Google receives from each of the bidder, any platform receives from each of the bidder in this case, is exactly the same across these two auctions. And just to summarize all of this in one simple picture, I present just one of the examples that we consider in the paper, where we have 5 bidders, 4 slots, different values of the players from 1 to 5. Click-through rates for the highest position is 20, for the second highest 10, then 5 and 2. And here on the very left, we see the values of the players from 1 to 5. In the next column, it is the VCG predictions, which is just the truthful bidding. So the bids are equal to the valuation in the competitive benchmark, and the EOS equilibrium for the GSP auction, in which actually the bids are mostly lower than the valuations of the players. All right. So now I think let me, without further ado, move to the simulation results and start with the case of independent players that use the algorithms in the GSP auctions. So since I'm going to talk about the results and present the tables in the very similar format, let me tell you what do we see on this picture. So as I've already previewed, we focus on 6 experiments, which we just took from theoretical literature on the GSP and VCG auctions. And these experiments are, each line is a different experiment, right? The result for the different experiment. Now, what do we see in the columns? The first 2 columns tells us the EOS benchmark. Both the bids of the players ranged from the highest to the lowest, corresponding to the players with the highest valuation first and then to the lowest, and the revenue of auctioneer predicted by the EOS equilibrium. In the next 4 columns, we see the results for the Q learners, and in the next 4 columns, the results for neural learners. So we will contrast often those 2, or some other algorithms. I will tell you a bit later about this. So in these 4 columns, we observe the bids to which the algorithm converged. Both of the algorithms converged. So the bids are also ordered from the bid of the player with the highest valuation to the bid of the player with the lowest valuation. And these are the average bids, because we run for each of these experiments, we run 50 runs for each of the line. And then we average across the runs, because there is still some variation across the runs to which we converge. Moreover, for different algorithms, we use the different number of iterations of the algorithms. We see much faster convergence, which as expected for the neural learners versus the Q learners. And we use 1.5 million iterations for Q learners versus 100,000 iterations for the neural learners. So the values that you see is just the average convergence values. The next
Ksenia,
yes.
Can I just a quick clarifying question here?
Absolutely.
So in each experiment, it's the same players playing sort of a very large number of auctions under the same valuations, everything the same. This is how you conceive of the Q learners and the neural learners to actually learn something, right?
Yes.
Okay, and so that's what you just said. You basically how often you play this depends on how fast these algorithms converge.
Yes. So basically, we assume that algorithms at first they engage in the exploration we actually use the random exploration for both of these algorithms. So first they explore, but then since the exploration decay, as a result, they converge to some particular values in the end. We also see a bit of cyclical behavior, but this is because the revenues are the same for different grid points across all possible bids.
There's a couple of other questions in the
Yes.
comments about the two different algorithms. So one question by Gonzalo Balestero is, how do you define convergence, whether it's the same as in the Calvano paper?
Yes.
It is, okay, great. And then Dominic Riss was asking a bit more about the difference between the Q learners and the neural neurals, which I guess is what Thomas was also kind of getting at. Is like, so are they, you know, like how much of a model, like do the neural learners actually have like a model of the bidding process, or do they, are they just trying to, okay.
Yeah, so the neural learners, the neural networks are basically first defined randomly. And then at every single point for the neural learners, we experiment with which bid to submit. Given the bids of the other players, we can see what would be the reward. So here we are actually similar to Calvano, meaning that we assume that the state variable, so what the algorithms know are the bids of other players. We also experiment with this, but for these tables, we assume that the bids of other players were observed in the previous period. Then the algorithm, the neural learners, what it does is among all possible actions, there is one vector which defines what actions were actually taken. And then there is another vector that tells you what would have been the optimal actions if you knew what the other bidders would submit. So this algorithm actually knows basically everything about the structure of the auctions. And if we knew the actions of other players, what would have been the optimal action? The complication here is that still there is experimentation, right? And every single learner changes the strategy at every single step. So it could be what was the optimal action at one point, compare in the particular state is different from what it would be further in the line. But yes, there is a experimentation, assuming that we know at each state after the action was done what would have been instead the optimal play. And then we see that after substantial number of iterations, the algorithm actually learn to play some strategy and they don't change their bidding behavior. Again, so maybe one note here. Again, there is a possibility of having a cycle because it could be that the best response is the same because we have this auction structure when several bids on the grid point is giving exactly the same rewards on to the players. And then, like instead, right, the Q-learning approach instead basically knows nothing apart from the reward, exact reward that that was algorithm got in one particular iteration, and then it use the random experimentation plus the knowledge about the previous actions that were optimal. So the value that algorithm assigns to the particular action changes from one state to another, but that's exactly very similar to how in Calvano the algorithm works.
Ksenia, curiously, experiment 6 looks very different from the others. Is there any intuition behind that?
Yes, absolutely. We exactly included it for that reason, because that's very tricky example when there is a multiplicity of not even efficient equilibriums. So that's the only one when we have many inefficient equilibriums, and we want to see, do the algorithms figure out what to do and what they converge to? And actually here we were surprised that, as you see in the, for the neural learners, they actually learn to play Nash equilibrium and even efficient allocation, while Q-learners apparently don't really learn much in these types of equilibrium.
And one other question, the number of slots in every experiment is fixed. something that, seems from casual observation to happen on search sites, Google in particular, is that the number of ad slots vary. Have you tried to see what would happen if you run an experiment, but the platform randomly, adds or subtracts a slot, whether that really disrupts the ability to learn?
Yeah, that's very good question. I think it's very interesting to try. We haven't tried yet, but we'll put it on our to-do list that is already, we have several things to do, but it would be one of the definitely very interesting things to look at. Thank you. All right. Yeah. If there are no other questions, maybe let me try to summarize the results that we got. And
excuse me.
Yes.
May I ask a question? Sorry, I'm Vitek from Crest, France. So can you help me understand what the neural network is doing? Because this is about the supervised learning, and I have little idea what it's trying to approximate. Like, are you using neural network to approximate the equilibrium strategy from EOS equilibrium, or what is this subjective function? Or do you know the true equilibrium strategy and you're using neural network to train this algorithm?
Yes, so the neural network exactly tries to train the algorithm to bid optimally given the changing bids of other players. So talking in the language of the neural network, we will have the input layer, which would take the bids by the other players in the previous stage, and then it tries to optimize the behavior of each of the players in the next stage. So we actually have 5 neural networks for every player. So every player has its own neural network, its own algorithm. It takes as an input the bids of others, as an output, what would be the optimal action to do given what we observed in the previous period.
But it is not an optimization algorithm, so there must be some supervisor who is labeling this.
Yes, exactly.
Okay.
Exactly, and then
so where does label comes from? That's my question. Like,
I see. So that's why this is the algorithm that actually we think about the algorithm that knows what would have been the optimal actions if we already observe what other players did. So it should know the auction rules, right? So there is the optimizer that after the bids already are submitted knows what would have been the optimal strategy instead of what neural network did in the previous stage. So we calculate the loss function, which we then minimize. It is dual entropy loss function, and we use Adam algorithm for backpropagation to minimize it.
Thank you.
Thank you. I'm happy to talk more about that for sure. Okay, so the results here are the following. I don't have too much time, so let me dive into that. The first result that we see here is that the neural learners, so the more informed algorithm compared to the less informed algorithm, is much better for the efficiency of the outcomes, right? So we see almost 100% efficiency versus much lower in case of the Q learners. So to take from here is that more information about the auction rules is better for the efficiency. Okay, the next result that I want to show you here is that apart from experiments 1 and 2, and I can talk about why we think it's the case, we see that the neural learners, so the more informed algorithm, lead to the lower Ksenia revenues than the algorithm that is less informed. So in experiments 1 and 2, it doesn't hold, but we see here that the lowest player bid higher than its valuation, which is actually a very risky behavior. And our guess here, and we now construct some experiments to prove this, is that when there is not enough slots for the neural networks, it's hard to learn all the strategy and to experiment, because it doesn't have all possible combinations of actions of other players. All right, so more information about the auction rules, better for the advertisers. And the last result from this table that I want to look at is that most of the players tend to be lower than predicted by the EOS equilibrium. And when we have enough information, the Ksenia revenues are even lower than the competitive benchmark that we consider.
So, sorry, just a really quick clarification question. The Q-learner has is not forward-looking in this story, or
so in this particular, we have simulations with delta equal to 0. In this particular, it's delta 0.95. Again, we started to look at this very broad and very different algorithms because we think that it's the most common approach if you look at the case when there is no information and in the case when there is all information about the auction rules. But then I have in the appendix tables for the other different discount factors. Yes, thank you.
So this is actually the opposite of the results of adaptive learning versus reinforcement learning in kind of competitive in like pricing, where adaptive learners should converge to the competitive equilibrium, but reinforcement learners can reach these like super competitive prices. So this is kind of the opposite of that.
So what we see here, it's exactly that. In these settings with different players, and so the papers that I'm aware of look at the symmetric players in the settings. So we definitely will experiment more to try to get to the essence of the results, but this is what we observe, right? Okay, so another test that we did is we looked at the differences in the initializations. So we could look at the Q-learners with different types of the initialization. If we initialize the neural networks in the completely random way for the Q-learners, we can initialize the algorithm in different ways. And some of these initializations could be more informative than the other. So it simulates the situation when the algorithm's starting point already has some information about the auction environment. And here, informed initialization, I mean that the players could understand how would be to bid optimally, knowing their own valuation and assuming that all other players just bid randomly. That already kind of tells us that the algorithm knows the number of players and what are the possible random bids of the other players. As soon as we introduce the more informed initialization compared to the less informed initialization, the results that we saw before also hold. So if we look at the red boxes here, we see that with the informed initialization, we have 100% efficiency and Nash equilibrium apart from this experiment 6 that we already briefly discussed. And in terms of revenues, same story. In most of the experiments, so basically in everyone, but the first one where the revenues are similar, the informed initialization leads to the lower revenues for the auctioneer than uninformed initialization. And this is just across the same Q-learning algorithm. All right, since we talked quite a bit about the GSP format, I wanted to show you just a couple of slides on the VCG in contrast with the GSP and see what's happening there. So the first results here is that we see that in VCG, actually the players bid lower than the evaluation. So it's far from truthful bidding in the VCG that we predict in the theory. And the second result is that we can see that the revenues are actually lower in the case of the VCG, for example, compared to EOS, but also compared to the GSP results that we get in case of the Q-learners. So let me, so here I just highlight the results of Q-learners. So it's same algorithm bidding for the in the GSP auction versus bidding in the VCG auctions. And the revenues in VCG tend to be across this broad variety of experiments, right? We see that different number of slots, players, and valuations of the players, they all tend to be lower in the VCG case. Now, in the last 3 minutes, I will tell you what do we get in our extensions. And the first one was the random player. The prediction was that we get efficient outcomes, and we were surprised, but it was exactly true that both in the Q-learners and neural learners cases, once we introduce the random player, algorithms learn much faster, and they are much more stable and have 100% efficiencies across the runs. The next extension was the agency bidding. In this case, we considered same experiments, apart from experiment 1, in which we just had 2 players, in which we have the agency bidding for the highest player with the highest valuation and player with the third highest valuation. So 2 bidders under the agency. And we want to contrast it also to the case of completely independent players. So what we see when agency is introduced, we expect that agency might tend to coordinate the bids of its clients. But the first thing that I want to show you is that once we contrast again the case of Q-learners versus neural learners, the results that were true for the independent players are also true for the case of agency. So we see that more informed algorithms tend to lower the auctioneer revenues in case with agency bidding as well.
And so, it's 4:45, but because there were a bunch of questions, I think we should just go until the end. But I just have a question about this slide. So the first set, so UCRAA, that's the non-algorithm, that's the optimal agency bidding.
Exactly. Sorry, I didn't mention this, but this is theoretical prediction of, again, it's one of the equilibrium, because here definitely there are very many, but it's a competitive benchmark that we looked at when the agency maximizes its profits of both of the clients, the sum of the profits, and at the same time satisfied several constraints. But I can share the paper related to that in case. Yeah. All right, and here I just used the chance to show you one graph of how the actual simulations look like. And we consider the experiment 3, the one with the 5 players, in which on the top, you see the convergence of the algorithm auctioneer revenue in case when we have independent players. And on the bottom, in the orange, we see the auctioneer revenue convergence over all the iterations in case when we have the agency bidding for the guy with the top valuation and the third bidder. And as you can see at first, actually the revenues are pretty much similar. There is a lot of experimentation in the very beginning, but then quite soon already the revenues start to be separating, and as a result, the revenues converge to the lower point for the case of agency bidding compared to the case of independent players. And just the last experiment, which I think it's really interesting to go in this direction, because this is the case when players are symmetric. So here we just tested, let's use the Q-learner with informed initialization for one of the bidder, and then all the rest would use Q-learners without informed initialization for the rest 4 players in experiment 3 with 5 players. So let's focus on what is in this box. And these are the individual rewards of the bidders. And the first line corresponds to the experiment when the first bidder actually was more informed. The second to the case when the second bidder was more informed, and so on. And what we see, both surprisingly and not, is that among all possible rewards that the first player got, he got the most when he was more informed compared to the others. And the same for player 2, where player 2 was more informed in the second experiment, and the reward across all possible rewards are also high. And we think that this is very important benchmark, and we plan to use different scenarios and experiment with different things when different players have asymmetric information. Would be really nice to see what would be the platform's incentives to use the more informed algorithm for their players when it also wants to maximize the auctioneer revenue. So that's also something that we are currently working on. So let me briefly conclude here so that we don't go much over time. And what I want you to remember from this presentation is that in our setting with GSP and VCG auction, we find that more informed algorithms improve efficiency and lower auctioneers' revenues. And at the same time, algorithmic bidding sustains low bids both under the GSP and the VCG. Moreover, the revenues under the VCG setting tend to be lower than those under the GSP. And this is actually, I think, very interesting and highlights the fact that there is different learning for these two algorithms since because of the reward structure. So, and the bidding structure. So what is the payment in the GSP? In the GSP, the payment only influences one of the other bidders, but your bid and payment in the VCG influences all bidders that are below you. So the learning can be different in the VCG scenario versus the GSP. And if we look at the theory, those two it doesn't matter in case of the just considering what would be theoretical equilibrium, but for policymakers, it could be interesting to take into account what is the learning in these two type of settings. And finally, for the extensions, we saw that the random bid improves efficiencies, the common intermediary lowers auctioneer revenue even further. And in terms of asymmetric information, more informed players earn higher rewards. Obviously, there are many possible outcomes that the platform itself could be influencing, and there could be a strategic auctioneer who influences the outcomes in these auctions by changing the reserve price, adjusting the quality scores, and so on. So we are also looking at these extensions as well. So thank you very much for having me here. And so here is my email. I'm super happy to answer any other questions as well afterwards.
Great, thanks a lot, Ksenia. So we have about 8 minutes left, and then I think we can stay a bit longer if people have other questions. So there's 2 questions in the chat. One from Yossi. So Yossi wanted to just get a bit of more of a. So let me just tell you them, and then you can answer. So Yossi wanted to get a bit more of the intuition behind the conclusions. So these are like facts, but he wanted to know, you know, what are the kind of economic mechanisms that are driving them. And then Gonzalo was asking about the mechanism that sustains low bids. So whether it's something similar, like, I guess the question is like whether the algorithms actually learn collusive strategies. I guess do you have like an experiment that's kind of equivalent to the Calvano experiment where, you know, like they reduce the price of one competitor and then show that the other competitor punishes them and kind of sustains these kind of, so there's something equivalent that you can do in this setting.
Yeah, thank you so much. I think that's a super important question. And I think I should have said a disclaimer in the very beginning that this paper is very much work in progress. So all your comments and suggestions are super welcomed. And we will definitely try to address all. So actually, exactly at this point, we are working on setting some experiments that can shed light on why exactly we have these particular results, right? What leads to these results. So I tried to tell you a bit more about the VCG and GSP differences, right? And this is something that I think we are more comfortable with to comment. And at that point, but we are working on different experiments that can explain us what tend to be able to sustain the lower bids than competitive benchmarks. So sorry that I was not as informative now, but we are definitely addressing this and working on
that. Thomas also has a question. Thomas, do you want to unmute yourself and then ask him?
I'll try. My internet's really poor today. So I was just wondering whether we should interpret the collusion, the sustained lower bids as overfitting to past bid behavior, right? So you only have a few bidders, right? And there's only so many things so the way I think about this, right, this could be like a constrained environment, right? So that the data that these algorithms get to update might, yeah, so that's how I think about it. I wrote, so should we interpret the collusion, the sustained low bits as overfitting to past bid behavior when only a few bidders are involved? Like if you want to take it back to machine learning.
Yes, so I think that definitely there is something in the environment of the specific algorithms. I wouldn't think that this is the case in case of neural learners, because there we literally tell every time what would have been the optimal strategy. So I don't think that it's overfitting there, but I would definitely consider it as one of the explanations in the case of Q-learners approach, since they definitely don't have, the exploration is decaying and they can be stuck in some particular behavior.
Yeah, but even with the neural networks, right? So like if you think of an equilibrium, then the equilibrium is in a way like taking into account all possible actions, right, of all the players.
Yeah.
And so when you think about what's ever realized, right, in this path to convergence of algorithms, it might not ever get to explore. So I view this as, you know, you never get to a view of the world that would be as general as sort of the equilibrium point of view.
Yeah. No, true, right? Because not on every iteration we consider all possible scenarios for other players, right? So I think for that, we could try to see the result with the maybe smaller an amount of bidders so that it's more tractable a bit, but to increase the experimentation, right? To see that we have enough of all possible combinations of actions of other players. But it's true that there is, since there are so many, especially when the number of bidders increase, then by observing only the outcomes of particular iterations, right, we cannot consider, right, all possible scenarios maybe enough times, because it's also changes, the behavior changes from one iteration to another. So yeah, that's a very good point. Thank you.
Yeah, maybe I can clarify a bit. Sorry, hello
yes,
everyone.
Michele, please.
I'm Michele Rigatti. So about the overfitting in the neural networks, actually, as Ksenia was saying previously, we actually define a label vector, through which we calculate the loss after the action taken from the algorithm in a particular state. But what is important to notice about this label vector is that by doing firstly the consideration that there are multiple available equilibriums, so multiple bits can get you the same reward, we define a label vector with that consider this. So every possible action that gives the optimal outcome is labeled as 1, while the others are labeled as 0. So I wouldn't think of the collusion of these neural networks as some kind of overfitting, because they have clearly space of actions. So they actually could decide amidst these possible optimal actions that are available, which action to take. So I don't know if this clarifies it better.
No, Michelle, thank you. I understand, and maybe what I said is misleading. So I'm not. I didn't want to imply that it's sort of overfitting to the data that is being produced. What I actually meant to say is that the data so as the algorithms produce data that they then use to learn more as they interact, they don't get to explore what sort of an equilibrium perspective would give you. So in that sense, the algorithms generate the data that they then, as they interact, right? And so so it's not, I shouldn't have said overfitting to the data that there is. It's just that the data doesn't when you try to work with that data that is being produced, you never get to sort of the full to this perspective that you'd have if you pursued an an equilibrium point of view. But so then the question is, where does this come from? How general is that, right? I mean, you showed that it breaks down if you have one noise trader. So would it also hold if you have, like, if the state space gets really large and you have lots and lots of bidders, or if those bidders, slightly change their valuations from period to period, or whether this is really just this sort of spatial case where everything, so the exact same people sort of interact repeatedly and a small number of people.
Yeah.
Oh yeah,
That's
definitely.
great.
That's a great
Thanks, Alex.
consideration. Sorry.
Sorry, guys. Yeah. So we're basically, so it's 5 p.m. right now, or 6 p.m. right now. So let's, Christian is just going to make an announcement about the next seminar, and then we can stay online and continue the discussion if people have more. I actually have more questions. So
all right. Yeah. Thanks everyone for coming. Really just a quick announcement. Our seminar will continue in 2 weeks. Next talk will be on May 19th. Speaker will be Rafaela Sandut from HDS. Thanks everyone for coming. Lively discussion, and then I hope the discussion continues. So see you in 2 weeks. Thanks.
Yeah, thanks to Ksenia and for everyone for the great discussion.
Thank you everyone for joining.
Yeah.
Very happy.